One application is average versus instantaneous velocity. So let's say we have a position function. This position function is usually denoted S of t. It tells us the position of an object at a time t. Okay? So that's the first thing we will use. We should also note again that the average velocity is the change in distance. Okay? This distance will come from the position function over the change in time. So really this just boils down to slope. That is, we will take, so if we're looking at the average velocity between a time t1 and t2, you evaluate the position at t2, subtract off the position at time 1, and then look at the change in time, t2 minus t1. So, for example, let's say we're going to drop a ball from 450 meters high. We want to find the instantaneous velocity at t equals 5, and we are given that the position function is 4.9 t squared. Okay. So first what we can do is let's find some points. We're looking for the instantaneous velocity at when t is equal to 5 seconds. If you put that into the function, we get a position of 122.5. So here's time, when time is equal to 5. And remember, this gives you the position, which the position in this case is the height of the ball. Okay. Now, we're going to use the average velocities to find that instantaneous velocity. So again, this is an issue where we're going to be looking at the slopes of the secant line and then take the limit of that to find the slope of the tangent line. And the slope of the tangent line at t equals 5 will be the instantaneous velocity. Okay. So now we can pick any other point to start our investigation. Let's say we're looking at the time interval between 5 and 6 seconds. When you put 6 in, we get a height of 176.4. Okay, so from there to there. And what we will be doing then is moving this time interval closer to 5 until we can see what is happening. Okay, so let's do that. So let's just make a nice little chart. Here's our time interval. And so we are first going to look what happens when the interval is in between 5 and 6 seconds. Then the average velocity is the change in the y values, 176.4 minus 122.5, divided by the change in time, 6 minus 5. And so what we find there then is the average velocity on that time interval is 53.9. We are in meters per second. Now, going back here, remember we're going to try and move even closer. So let's get pretty close. We could say, all right, what's happening here at 5.1? All right. So now our time interval goes in between 5 and 5.1. So you would put that in and you would find the position at 5.1 and subtract off the position at 5. And now the time interval in between there is 5.1 minus 5. And when you come out with that, you should get 49.49 meters. That's a 9 meters per second. But let's get closer, right? We could come even closer. Let's look here. So let's say that's the time interval between 5, starting at 5, and now going to 5.01. Okay. So again, we do the same thing. The position at 5.01, we subtract off the position at 5, then the change in time, 5.01 minus 5, and when you do this, you should get 49.049. This is meters per second. And we could just keep going. Let's say we want to go 5 in between 5 and get even closer, 5.001. If you follow the same, what you should come up with now is 49.0049. So what can we say then? As we look at these values, what's happening? We start at 53.9, we go to 49.49, then it's 49.00 or 0.049, and then it's 49.0049. And what we can say then, as t approaches 5, and we're approaching from the right-hand side, the position function, or not the position function, I'm sorry, the average velocity is approaching 49 meters per second. So the value that the average velocity is approaching is the instantaneous velocity. So we will say that the instantaneous velocity at t equal to 5 is 49 meters per second.